So let us go for the second talk of this session by Professor Eknath Ghate on modular representation theory using calculus. Please.
Thank you, Professor Washford. Thank you to Anuj and Ajaban and Shauli. See some of them here for the invitation to speak here. It's lovely to be back here. My talk is more on the algebraic number theory side, so sorry for the phase shift, but there's some calculus in it, so hopefully that's a transition from analytic to the algebraic world. But there's some finite fields there, and they showed up in Professor Abhikari's talk too. So this talk may look a little isolated, but it's part of a larger program I have to use the Pierre-de-Langlands correspondences to compute some information about Ghate representations. So I won't be able to say much about that in this 30 minutes, but you can treat this talk just as sort of independent facts from representation theory of GL2FQ, GL2 of finite field. But the vector spaces on which this group is acting are going to be vector spaces defined over finite fields. So it's what's called modular representation theory. So the characteristic of the field over which the representations are defined is the same as somehow that characteristic divides the order of the group also. So a little unusual. Okay. So we start. So that dr. So we saw some symmetric powers already earlier today in Kanenika's lectures, but here are some symmetric power representations of this matrix group, but we have a model for it in terms of polynomials. So let's look at all polynomials. This is sort of going to be high school mathematics. Homogeneous polynomials of degree r in two variables defined over a finite field. Sometimes we just take the field P, Fp, sometimes I'll take Fq, sometimes I'll take Fp bar, the algebraic closure. Let's be simple and start with Fp here. And the group GL2Fp, let's slow things down a bit and start with the finite field with P elements rather than Q elements. This acts on such polynomials. If you have a matrix, and it just moves the polynomial around by moving the variables around. Okay, so that's a natural vector space. You're just making the group act by changing the variable, substituting, and then we get a new polynomial. So this is a nice modular representation of GL2Fp, and it's a classical theorem. I was trying to look up the exact reference. Oh no, this is exactly correct, but let's say Brouwer-Nesbitt from 1941, there's an analysis paper, which says that this representation is irreducible only for small values of r, more precisely, if r is between 0 and p minus 1. In fact, this is almost a complete list of the irreducible representations, up to twists by the determinant powers. So up to twists by determinant powers, this is actually a complete list of irreducible representations. So this is one fact. And so what happens, for example, if you take r to be p, you take polynomials of degree p, indeed, if you look at dp, so this is polynomials of degree p, then if you're teaching calculus or algebra in the US, something called the freshman's dream. So x plus y whole to the power of p, many people expand that as x to the p plus y to the p. But that's actually true in characteristic p, right? So if you look at this subspace spanned by these two monomials, right, and you put ax plus cy to the p here, all the middle terms will die and that space will be stable. So that shows you that polynomials of degree p have this subspace, so this is not an irreducible representation. Okay, so that's why that fails. And a bit more interestingly, if you look at the r for r bigger than p plus 1, then there's a famous polynomial called the Dixon polynomial, which is the following. It's called theta x to the py minus xy to the p is a prime, of course. I have to say that here. If you look at this polynomial and look at all polynomials which are divisible by this polynomial, so space generated by theta means theta times q, so p is theta times q, then this is also stable because this particular polynomial, again by the freshman's dream and things, this polynomial is stable by the action of GL2FP. The determinant comes out as a constant, it's a small computation, and you wind up just with the theta polynomial times some scalar to make a GL2FP act on it. So again, this is not zero, and this space is therefore reducible. So it's reducible even for r bigger than p plus 1. Okay, so good. So what you could do then is look at the following quotient. So maybe proposition. This goes back to University of Chicago thesis. You took Glover, 78. You can look at the remainder, space of remainders. Let's call this space, sorry, this is the R1. The typos, please tell me. So polynomials which are once divisible by theta, that's a subspace of all the polynomials. Look at this quotient, VR mod VR1. And he proved using literally high school methods, define, there's some, basically some x's and y's here and some x's and y's here. The degrees of polynomial are here. Here the degree is s. He mapped particular monomials to particular monomials, and he came up with a GL2FP equivariant map, an isomorphism, which respects the GL2FP action on both sides. He proved this if R is going to S mod T minus 1. So that looks somewhat interesting. It's a sort of a periodicity result of some kind. R and S are getting larger and larger, but as long as they're in the same covariance class mod P minus 1, then these quotients are isomorphic. So there's this sort of elementary proof of Glover, but nowadays is an observation due to Sandra Rosenstein that you could sort of prove this in just sort of one line, so to speak. If you observe that this space is actually an induced space, so if you work in group theory, you know what induced spaces are, but maybe I'll define it. So let me just let you stare at the notation first. So this is the induction from the Borel subgroup. So this is the space of upper triangular matrices in GL2FP. A, B, D are infinite field, AD non-zero. So this is a subgroup of that, and you're inducing a particular character. The D to the R character takes this matrix A, B, 0, D to D to the R. So it's called the D to the R character. You take the lower right entry and raise it to the earth power. Okay, and what is the definition of such an induced space? Maybe I'll just define it here. So in general, if you have induction from H to G of so if V is a representation for H, this space has a model. You can just think of it as functions from G to V, which satisfies some invariance property. So it's all functions, subtheoretic functions from G to V, such that f of Hg is H dot f of G, and this is the, we use a representation for H, so this is a group action. It's a vector in the vector space. Okay, so that's just the definition, and the group acts on the right by right translation. That doesn't mess with the property we have here on the left. So that space is stable under right translation. That's the induced representation. So again, a representation of H, you immediately get a representation of G by induction. And if you look at this particular induced representation, it turns out to be isomorphic. So it's not so surprising here because the index of this is P plus 1. and this is the space of all remainders dividing by a polynomial of degree p plus 1. So this dimension is also p plus 1, finite dimensional space. Both these things have the same dimension. That's easy to see. Why does this imply that? Well, this character is periodic mod p minus 1. If you take a non-zero element of finite field and raise it to the r power, if r is going to s mod p minus 1, r is going to s mod p minus 1, then d to the r is equal to the d to the s, right? So this you can replace d to the r by d to the s and then reverse this isomorphism with s, and you might immediately get the previous result. So that's nice, and maybe I should say what this map is. So given a polynomial, I don't have much space here, but let me write it here anyway, so you don't have to erase what's below. Given a polynomial p here, you want to define a function, right? There's a space of functions. So which function do you sort of a nice, very nice function? You send a matrix ABCD in the group GL2FP to a vector. Now this is a one-dimensional representation. So you send it to the lower, you evaluate the polynomial at the lower row of the matrix. Okay, so this is the element in FP. Polynomial is defined over FP. Just evaluating the polynomial at the lower row. You can check many of these little things hold, that it's invariant under H and things. Okay, so just evaluation of a polynomial at the lower row. Okay, so now we understand that Glauer's result can be recovered by just recognizing this space of remainder polynomials as an induced representation. Okay, any quick questions while I'm erasing? Okay, so this was about the history of the subject until I started looking at this with postdoc Ringam Jana at the IFR until recently, and now has moved to Mysore Bherampur. So here is some generalizations. You just sent the proofs in yesterday, but maybe it'll appear next year. So what about spaces where the polynomial, where your polynomial is divisible by higher powers of theta? So let's define that space, Vr m plus 1, to be the subspace of Vr generated by theta m plus 1 at powers of theta. Can you do something a bit more, for example, for polynomials which are twice divisible by theta? Okay, so here is some facts. So when m is equal to 1, we prove that this space is isomorphic to another induced space. By the way, these representations are called principal series representations, some nomenclature. After the Borel induced up to G of the group, called a principal series representation. So these are a bit more sophisticated than principal series. It's not really a one-dimensional representation you're inducing, a two-dimensional one. So okay, so what are you doing here? You're looking at V1. V1 is just AX, linear polynomials. Polynomials at x and y, linear, AX plus CY or something. But you're restricting that representation to Borel and twisting that by this character, which is already defined over there. And then you're inducing that up, as in that definition. And you wind up getting this particular quotient. And it turns out that this is not always true. You have to assume that P does not divide R. R is the degree of the polynomials. Okay, so this looks like a slightly strange fact, but what is interesting is that this map is an explicit isomorphism. So given a polynomial, we have to give a function which to a matrix takes an element, a linear polynomial. So let's just say it has two coordinates. And what are the two coordinates? Turns out the coordinates are 1 over nabla, P, CD. So remember, in this case, it was just evaluation of the polynomial. It was just a one-dimensional thing. And now you have a two-dimensional thing, you have two coordinates. So in the second coordinate, you just evaluate the polynomial as before. But in the first coordinate, and this is where some creativity came in, we differentiate the polynomial with respect to a Nabla operator. There's some calculus happening in algebra, which is unusual. Divide by r, that's the condition that p does not divide r, and then evaluate at CD. So what is Nabla? Nabla is a ddx plus b dy, partial derivatives. Okay, so you can prove something like this. There's another result where what happens if p divides r? Well, then you have to massage the other side a little bit. You have to replace this representation by a split representation. So let me not get into that, and you have to modify that Nabla operator a little bit. Let me continue generalizing this. Suppose that now m is even more general. We did m equals 0 over there, m equals 1 is over here. Let's look at Vr mod Vr m plus 1. So I did the m equals 1 case separately just to lessen the load on the notation. But suppose that p doesn't divide the binomial coefficient r choose m, then this is isomorphic to, again in induced space, dr minus m from the Borel to GL2FP. So this space you're inducing gets a little bigger depending on m. You twist by a character which also depends a little bit on m. And then you induce up. And the definition of this map is very similar to this one. There's many more coordinates, and there's some binomial coefficients that appear here. And that's where you use this fact that p doesn't divide r choose m. Okay, so but there are many more Nabla operators, powers of Nabla operators and things. Maybe I'll skip the exact definition. Okay, so a corollary of this is that you get a more general kind of periodicity for these quotients of symmetric power representations, these generalized remainder spaces. This is something that I was looking for with another ex-student, our postdoc at ISC Bangalore, Ravi Teja. And we managed to prove some things using some dual numbers, but this is a little sharper than this and more simple to prove. So corollary, whenever m is between 0 and p minus 1, and p doesn't divide two binomial coefficients, r choose m and s choose m, and r is belonging to s mod p minus 1, then the spaces of remainders are isomorphic. Again, the proof is evident from here. This is independent of r. That's the key point. There's a Vm here. M is fixed. The only slight dependence on r is the power of the character, but if r is going to s mod p minus 1, this character is the same. D to the r minus m is equal to d to the s minus m. So you immediately get this. Okay, so the title of the talk was GL2FQ, not GL2FP. So let me state a further generalization of this. So now suppose you're working with a finite field with p to the f elements. F is any number bigger than or equal to 1. Then, okay, so let me first tell you what the irreducible representations are essentially. So again, the same paper, Brower-Nesbitt, says that you take tensor products Okay, so what is this? These are just spaces of polynomials, but now there are many variables. Each of these is, for example, this is an x0 and y0, polynomials at degree r0, and x0, y0. These are an x1, y1. These are an xf minus 1, yf minus 1. GL2f qx. Maybe I won't write it down, but GL2 FQ doesn't act diagonally on the polynomials. What you do is there's the Frobenius map, right? FQ has a canonical Galois automorphism, x goes to x to the p, which takes FQ to FQ. So what you do is when you have a matrix, you first make Frobenius act on it. A, B, C, D goes to A to the P, B to the P, C to the P, D to the P, and then make it act on that factor. Do it Frobenius act twice and on this factor, etc. F minus 1th power, and then you make it act on the variables on that factor. So you have this huge tensor product, and GL2FQ is acting on these tensor product in this way. Turns out that these are more or less exactly a complete list of the irreducible representations, up to twist by determinant again, they're all. And one can ask if there's a similar theorem for the remainders, and indeed there is. So up to this point, the theta polynomial was discovered by Dixon, etc., and is very classical, but checked in the literature, there were no analogs of the theta polynomial in the literature for GL2FQ. So we had to invent something. And we came up with the following result. All these are the principal series section of that paper. So let the mi's be small. I is between 1 and f minus 1 each time, or maybe 0 and f minus 1. And the ri's are a bit large now. There the r's are small. Here the r's are big. I guess this is just extra general culture. Just introduce this so that you see this notation. But back to the lecture, the theorem is that if you take this tensor product and mod out not by the powers of one particular theta polynomial, but a whole bunch of them, then you wind up getting an induced representation. This time you take the Borel of FQ, upper triangular matrices, GL2FQ, and it's very similar to the previous theorem. Instead of Vm, you have a whole bunch of Vmi's. You tensor them all together. And Borel is acting by Frobenius powers on each of these, and you twist with d to the r minus m. And here p does not divide any of these binomial coefficients. None of these binomial coefficients. P doesn't divide r choose mi for any I. D to the r minus m is a shorthand for d to the summation ri minus mi p to the fi p to the j, p to the I equals 0 to f minus 1. So d to some power, but you take all possible powers ri minus mi, but with appropriate powers of p and add them all together. Take that character. So this is all obvious notation. Similarly, you have the Borel for GL2FQ. Okay, and you immediately get, so what are these polynomials? So here, theta I took a lot of sort of messing around with computations to come up with this, but turned out to be something quite simple. These polynomials are these polynomials. So it's a negative of the previous one, but the key point here is that the variables are sort of interlaced in this weird way. You have xi and then yi minus 1 to the p, etc. Okay, and then you get a periodicity results. Any such quotient will be isomorphic to any other such quotient with s's everywhere, as long as p doesn't divide all the rmi's and all the r choose si's, just because this space on the right side is independent of r and s completely, except for in a very weak way. But if the R and S are the sum of Ri p to the I is congruent to S, which is the sum of the Si p to the i's, then this character will be the same, and you'll get that these two quotients will be periodic. For large R, the remainder spaces only depend on the congruent class of R mod Q. Q is p to the F, p to the F minus 1, Q minus 1. Okay, so this particular statement is expected to have some applications to compute. Whatever I do in my life, there has to be a modular form somewhere in the background. So I know this audience is in love with modular forms, and so am I. So if you take a Hilbert modular form and you have its Galois representation and you want to reduce it mod p and you want to study what the shape of the Galois representation is, you need to, when you transfer this by the Langlands correspondences to the other side, you need to understand such quotients. And knowing periodicity and things like that, knowing that these things are principal series, etc., is very useful. So let me just leave it at that. Am I over time already? No, what time do I? Oh, I have 5 minutes, great. Good, so I can talk a little bit about the cuspal case. So this is so much for the principal series case. Let me say something now about cuspal representations. So if you're a little bit familiar with these matrix groups, then you'll know that there are essentially two families, interesting families of representations. There's the principal series ones and the cuspal ones. And they're kind of dual to each other in some sense. These have dimension p plus 1, those have dimension p minus 1. In the middle, you have the Steinberg representation, this isolated thing. And of course, you have the one-dimensional representations. So there's another side of the picture, the cuspidal side. Let me see if I can say that in a few minutes. So let me make a little remark here before I do that. Variant. Let me go back to the very first theorem, VR mod VR1. And let me multiply, tensor that with Vp minus 1, another space of polynomials. Then I would have to take the character induction d to the r. So if you remember, there's a Borel here, the Borel of Fp to GL to Fp, the very first result I stated. If you tensor both sides with Vp minus 1, it turns out you can move the Vp minus 1 inside to come up with a bigger space. And what you do is you put the split torus here. So this is just the diagonal matrices inside GL to Fp. So this is just a immediate corollary of that. I want to state this because the cuspidal things will be stated in this language. So let me get to the cuspidal case. So the reason I introduced this torus is there's another torus inside GL to Fp, another abelian group, which is the non-split torus. You take a quadratic extension of Fp, take its non-zero elements, and it sits in GL to Fp, just like the complex numbers sit in 2 by 2 matrices of the reals. U plus V alpha goes to this matrix, U, V alpha squared, V, U, where alpha squared belongs to Fp. Alpha does not belong to Fp. Just take any element of the finite field, take a square root of some element. That will generate the quadratic extension of degree 2. And you look at this is these 2 by 2 matrices. This is a bijection with these elements. So that's another abelian group sitting inside GL to Fp. And let me define omega 2 to be the character, which is the identity character. Okay, so really there should be a matrix here. This is a character of the group GL to Fp, or of the torus, sorry, of the torus. So I'm just taking it to U plus V. This is more or less the identity character. So here is the cuspidal analog cuspidal theorem. So remember, on the right-hand side, we had principal series kinds of representation. On the left-hand side, we have quotients of symmetric power representations. We want to follow that kind of model. So what if we induce, let me write the answer first, induce from the non-split torus GL to Fp of omega 2 to the r, right? This character, This is a non-split torus. That's these matrices. You induce that up to GL2FP. Well, it turns out that this is isomorphic to a quotient of a symmetric power representation. It's a quotient of D. So this is for 2 less than R less than P minus 1. Okay, so what's going on here? Let me be very quick. So here we have a larger symmetric power representation, polynomials in 2 variables, but of degree R plus P minus 1. D is not a particular polynomial. Now it's a differential operator. This idea goes back to Serre. It's x to the P ddx plus y to the P dy. You can check that the dimension will be P minus 1 when you differentiate this way. And the codimension there will be P minus 1. And I'm tensoring artificially with Vp minus 1 like I did over here. And it turns out to be an induced space, something like this. So again, this is given by a very particular map. I'll just write it in if I can. It's hard to write this, I think, in this much space. My handwriting is going to degenerate, but I'll try. But nabla alpha is okay, so just to give you a flavor of what this looked like, again, given a polynomial, I have to give you a function. And what function do I take? I take a matrix ABCD, I differentiate it R minus 2 times with respect to a yet another differential operator, nabla alpha, which has some A plus C alpha, B plus D alpha in front of it, and evaluate at the, so what's interesting here is now that was sort of differentiable calculus from the dual world of the cuspal representation, some sort of integral calculus coming in. You're evaluating this differentiated polynomial at 2 points and subtracting the evaluation at these 2 points. Like when you evaluate a direct limit integral, what is it called, a direct integral? Something similar like this happens. And then there's some fudge factory here, the q's. The q's are not so important. So again, one can prove such theorems using explicit differential operators. I should say that this representation is a cuspidal representation, tensor Vp minus 1. Just like in the principal series, you can pull out a Vp minus 1 and you get the usual principal series. Now you get a cuspidal representation. This is a notation I haven't defined. It's almost by definition. And so you can cancel Vp minus 1 on both sides of this isomorphism. And this theorem was actually proved before our theorem, so it's a stronger theorem. Our theorem follows from that theorem. But the proof is very technical. Uses crystalline cohomology. So I had asked Arindam to try and prove our theorem after tensing with Vp minus 1 just using calculus and no fancy crystalline cohomology. And so that is a corollary of that. And there's a GL2FQ version of that also, which I won't write down. So, thank you.
Thank you very much. Any question?
Yes.
Yes, please.
So how far are these from getting a Jordan-Holder, understanding the Jordan-Holder series of these representations?
Yes. So actually the principal series for GL2FQ generically has 2 to the F Jordan-Holder factors. At the socle, there's one particular weight. At the co-socle, there's one particular weight. And then it's sort of a diamond. Looks like Pascal's triangle, but 2 Pascal's triangle. I mean, there's one weight and then 2 weights. That's the socle filtration. So there are 2 to the F weights. And that's exactly where that was known. In fact, it's due to some Indian mathematicians, I think. Students of Bhamma Srinivasan. Maybe from Chennai also. So those results are well known. But if you transfer those results using this theorem, you get the Jordan-Holder decomposition of this. And that's what's useful in our computations. I don't know if anyone's tried to write down. Yeah, of course, there's not much to do there. It's one dimensional. So the Jordan filter factors are not so interesting there.